So welcome everyone. I know we're running a little late. I'm so sorry. This is session 10. Each speaker is going to get like about 10 minutes. I'm going to give everyone like a 1 minute warning that they're running off. So in this session, we have 5 great papers that do all new things in the spirit of ITCS. The first 2 are individual fairness and advertising auctions through inverse proportionality by Shuchi, Chawla, and Meena, Jagadeesan, and on fairness and stability in two-sided matchings by Gili, Karni, Rothblum, and Yona. And they are papers that I would say offer new lenses on core AGT problems like ad auctions and matchings. And the next 3 papers are the Nash-Bargaining-Based Models for matching markets, one-sided and two-sided, Fisher and Arrow-Debreu, Mojtaba, Hosseini, and Vijay, Vazirani. Then interactive communication bilateral trade by Jieming, Renato, Paes, Leme, and Kangding Wang from Duke. And the last one is multi-channel Bayesian persuasion by Yakov Abichenko, Talgam-Cohen, Haifang Zhu, and Konstantin Sabarny. So I think these 3 papers offer new models to get around some impossibility results. I had a couple more things to say about each paper, but since we're running a bit late, I'll just hand it over to our first speaker, who is Meena Jagadeesan. So Meena, if you can share your screen. Thank you.
Can you see my screen?
No.
Okay, cool. You can see my screen. Okay, so I'm going to talk about individual fairness in advertising auctions through inverse proportionality, and this is joint work with Shuchi, Chawla. So there's been lots of evidence of skewed delivery in online advertising. So people from different gender and racial groups can end up seeing differing amounts of ads in sensitive categories like housing and employment. Before I dive into how these sources of unfairness can occur, I'm going to give a very simplified overview of ad auctions. So the idea in an ad auction is when a user arrives on the platform, bids are collected. So either these bids are directly specified by advertisers or done through some sort of automated bidding system where the platform generates bids based on advertisers' high-level preferences. So after the bidding step, the platform runs some sort of an auction format to determine which advertisement to show the user. So some common ad auction formats that are used are either a first price auction, where the auction allocates the highest bidding advertiser and charges them their bid, or a second price auction where the auction again allocates the highest bidding advertiser, but then charges them their second highest bid. So what's a little surprising is that these standard ad auction formats can actually introduce unfairness into which users see which ads. So the first source of unfairness is that the advertiser targeting is unfair. So maybe the advertiser's bids actually look unfair. And this can kind of be audited by looking at each advertiser's bidding patterns in isolation. The second source of unfairness, which is more subtle, is that the platform's allocation algorithm can create unfairness even when the bids are fair. So even when each advertiser bids fairly in isolation. So this has been documented in various empirical studies. For example, in employment, it's been shown that there can be skewed delivery in ads even when each advertiser uses gender neutral targeting. And a similar phenomenon has been showed for housing ads. So in these settings, unfairness arises solely from the allocation algorithm. So our contribution is a fairness framework that eliminates the unfairness introduced by the platform. So we focus on this second source of unfairness, and we build on some previous work. So to get some intuition for why the platform can introduce unfairness, let's consider the following toy example. So consider 2 users, Alice and Bob, and 2 advertisers, a big tech company and a startup. So let's say that the big tech company and the startup both place very similar bids on Alice and Bob, but maybe the big tech company places a slightly higher bid on Alice and the startup places a slightly higher bid on Bob. So if maybe the platform runs some kind of standard auction format to allocate the ad slots, then Alice will end up seeing the big tech company ad and Bob will end up seeing the startup ad. So here the highest bid wins auction exaggerated these small fluctuations in bids. So these 2 users who receive very similar bids can end up seeing very different ads. So we show that these fluctuations are not just theoretical and actually can occur on the Yahoo Ads data set. So while I'm focusing on unfairness that can occur within a category of ads, there can also be unfairness from cross-category competition. So in this work, we focus on the unfairness from a single category, but our results here can be composed with results from existing work to get these multi-category fairness guarantees. Okay, so in our model, there's a universe of users that arrive sequentially. And when a user arrives on the platform, each advertiser places a bid on the user. So we can think of each user as associated to this vector of values. The auction then allocates a single slot per user, randomizing across the K advertisers. And we assume that this our allocation algorithm satisfies weak monotonicity, so it can be implemented in some incentive compatible way. So our contribution is ad auctions that do not introduce unfairness. And in addition to fairness guarantees, our ad auctions achieve a constant fraction of the social welfare compared to the unfair optimal. So this is the benchmark of what the maximal social welfare that can be obtained in the absence of any fairness constraints, and also achieves near optimal trade-offs between fairness and social welfare. So in this sense, the first point shows that the cost of fairness of these ad auctions is not too high. And the second result shows that these ad auctions are kind of near optimal. Okay, so the way we formulate fairness is as a stability constraint. So our starting point is individual fairness, which requires that similar users obtain similar allocations. And we formulate this fairness requirement as a stability constraint. So recall that we were focusing on the second source of unfairness, where the advertiser bids have already been audited to look fair in isolation. So now two similar users should receive similar bids from all advertisers. So our stability requirement is if two users have similar values from all advertisers, then they should end up receiving similar allocations. So more formally, an allocation is value stable with respect to a value stability constraint if for every pair of value vectors, the following constraint is satisfied. So let's say that the two value vectors are coordinate-wise at most an alpha multiplicative factor apart. Then we require that the allocations are within a f of alpha additive factor apart. So we measure closeness for values multiplicatively, so that this is like kind of a scale invariant notion of closeness. And we measure closeness in allocations additively to capture the difference in probability that the two users see the ad. And so this function f captures how strong the value stability constraint is. So in some sense, how strong the fairness constraint is. And so essentially this guarantees that the auction itself does not introduce any further unfairness other than what might already be present in the advertiser values. So in this sense, we are focusing on that second source of unfairness that I mentioned in the previous slides. Okay, so with this definition in mind, our goal is to design value stable allocation algorithms. So if we look at the standard ad auction formats and consider this highest bid wins allocation, where we allocate to the advertiser with the highest value, this achieves the optimal social welfare, but it is not value stable. So the issue with the highest bid wins auction is essentially that the allocation rule wasn't smooth. So if we consider proportional allocation, this is kind of the most natural smooth allocation rule where we allocate proportionally to the values. This is value stable, but unfortunately the social welfare can go to zero as the number of advertisers goes to infinity. So the approximation for social welfare in this sense is very poor. So we design a family of allocation algorithms that are value stable and achieve a constant fraction of the social welfare regardless of the number of advertisers. So our solution is inverse proportional allocation. The key idea is to deduct proportionally to the inverse of the values. So we start by allocating the full ad slot to all advertisers and then deduct proportionally to the inverse of the value that that advertiser places on the user. And then when an hits a zero allocation, we kind of throw them out and then continue with this process. So essentially, we're setting T so that this equality is satisfied. And we show in the paper that this can be computed efficiently. So we also generalize this to deducting proportionally to functions of the values to capture a broader range of value stability constraints. So our main result is that inverse proportional allocation is value stable with the following value stability constraint and achieves the following approximation ratio. So in particular, if we set L to be 1, this achieves a constant fraction of the social welfare compared to the unfair optimal. We can tune the fairness social welfare trade-off as we change L. And it also achieves near optimal trade-offs between fairness or value stability and social welfare. So regardless of the value stability constraint, as long as it satisfies a mild condition, there exists an inverse proportional allocation algorithm that achieves a near optimal approximation ratio for social welfare. So in conclusion, we considered fairness in ad auctions and designed ad auctions that don't create unfairness in the allocation. And we proposed a fairness notion of value stability, which guarantees that if the bids are similar, then the allocations are similar, and allowed us to isolate this source of unfairness created by the platform. And then we designed this family of allocation algorithms that achieve near optimal trade-offs between fairness and social welfare. And our results extend to broader notions of fairness. Thank you.
Great, thank you, Meena. So while the next speaker sets up, so Gili is speaking up next. If there's any questions, this is a good time to ask. I have a question, which is if you've looked at what would happen if you wanted to allocate more than one slot in this paper, right? You could imagine like a similar water filling algorithm like the one you proposed, but instead of having the constraint like you had it would be equal to 2 so long as you don't allocate more than 1 unit.
Yeah, that's a great question. So we could, you can kind of naively apply this for every slot and get some sort of guarantee, but it's not clear that when you restrict to there being every ad being shown at most once, that this is kind of going to be the right auction format. So in this work, we focused on single ad slots, but that would be a very interesting direction for future work.
Got it. Can you stop sharing us so that Gili can transition? Thank you. There we go. Great. So our next speaker is Gili Karni from the Weizmann. She's going to tell us about fairness and stability in two-sided matchings. Gili, all yours. I'll time you.
Hi, my name is Gili Karni, and I will present the work on fairness and stability in two-sided matchings. This is a joint work with Guy Rothblum and Yona from the Weizmann Institute. Our work focuses on the setting of two-sided matchings proposed by Gale and Shapley. The objective is to find a full matching between two sets of the same size. As the running example, we consider the allocation of doctors to hospitals for residency, where each hospital is matched to a single doctor. Each doctor has a preference over the hospitals, and each hospital has preference over the doctors. For instance, for this valid doctor, the preference is a yellow hospital, then blue hospital, and then white hospital. Similarly, the yellow hospital has preference over the doctors. We call this type of preferences ordinal preferences, and the goal is to find a matching that is stable. A stable matching is defined by the absence of blocking pairs, where a blocking pair is a pair of a doctor and a hospital that prefer to be matched with each other rather than with their matched partners. Consider this matching. In this case, the valid doctor and the yellow hospital form a blocking pair, and this matching is not stable. This notion of stability was introduced in the seminal work of Gale and Shapley, who showed that a stable matching always exists and can be found efficiently. In our work, our goal is to find a matching that is not only stable, but also fair to the doctors. For example, the matching should not discriminate doctors based on their ethnicity. Even without formalizing the fairness requirement in this context, one issue is that the preferences of the hospitals might not be fair to begin with. Suppose some hospital discriminate doctors from some ethnic group. In that case, requiring a stable matching might lead to a matching that is discriminatory against that ethnic group. However, are fair hospital preferences enough to guarantee a fair matching? In this work, we show that even fair hospital preferences do not guarantee a fair matching. And our main question is whether fairness and stability are compatible. To begin, we consider a limited setting where we assume a simple fairness constraint and fair hospital preferences. Based on these assumptions, we present two results. In the first result, we show that even under a strong fairness assumption over the hospital's preferences, simply running the Gale-Shapley algorithm is not sufficient to guarantee that the final allocation is fair. In our second result, we present an algorithm that guarantees both stability and fairness under these assumptions. This algorithm has a propose and reject structure that is inspired by the Gale-Shapley algorithm. In the last result, we show that if the assumptions are even partially removed, no Gale-Shapley style algorithm is able to achieve both fairness and stability. In order to show our results, I will first define what is our definition for a fair matching and for fair hospital preferences. I will start by defining what is a fair matching. We assume the doctors are partitioned into clusters, where in each cluster the doctors are similar in terms of merit. Our fairness requirement builds upon the approach of individual fairness proposed by Dwork et al., which says that similar individuals should have similar outcomes. However, we want to take the preferences of the doctors into account as well. Therefore, we use preferences-informed individual fairness proposed by Kim et al., which under the assumption of a partition of the doctors into similarity clusters, means that within each cluster, the matching is envy-free. That is, every doctor prefers its own allocation over the allocation of any other doctor in the cluster. The problem is that since the number of hospitals is limited, a deterministic fair matching might not exist. Suppose there are only two similar doctors and they rank the same hospital first. Since they cannot both be matched to it, any deterministic matching is unfair to one of them. This can be solved by matching each of them to this hospital with probability half. Thus, we would like to find a probabilistic allocation, that is, a distribution over matchings, and our fairness and stability requirements are a priori. Next, I will present our definition for fair hospital preferences. We say the preferences of the hospital are fair if the hospital has strict preference over the clusters and is indifferent between doctors in the same cluster. The definitions I presented here are a simplified version of the definitions we use in the paper. In the paper, we also define stability for a probabilistic allocation. Now that I presented all the definitions, I will present the results. As a first step, it makes sense to require fair hospital preferences and then to apply the Gale-Shapley algorithm to these preferences. A natural assumption is that if the hospitals are not discriminatory, the matching won't be discriminatory as well. The question is how to run the Gale-Shapley algorithm over such fair preferences. We use a probabilistic representation of the preferences and sample them. The preferences are represented as a distribution over ordinal preferences with a deterministic order of the clusters, where the order of the doctors in each cluster is chosen uniformly at random. We find a probabilistic allocation by sampling this distribution of each hospital preference and running the Gale-Shapley algorithm over the sampled preferences. The probabilistic allocation is the resulting random variable. We hoped that the fairness of the preferences will imply a fair allocation, but actually it did not. In the paper, we show two counterexamples for the two variants of the Gale-Shapley algorithm, where the preferences of the hospitals are fair, but the resulting allocation is not. This result joins existing works by Dwork and Dilvento that show failure of composition in fairness. That is, even if the mechanism seems unbiased, requiring fairness from all the participants is not enough to guarantee a fair solution. However, we do have a positive result. In the paper, we show an algorithm, fair propose and reject, that under the setting of a partition of the doctors into clusters and fair hospital preferences, finds an allocation that is both fair and stable. The algorithm is based on the structure of the Gale-Shapley algorithm. The difference is that the hospitals decide whether to be matched to similar doctors simultaneously, in a way that will maintain fairness. This is done by allowing the parties to propose and accept probability mass. The algorithm does not always stop, but it does always converge. Thus, we stop when the solution is close enough to a fair and stable solution. This is why the solution is approximately fair and stable. Dwork et al. Suggested formulating a fairness requirement using a similarity metric where distances are real values. The partition to clusters is actually a simple case of a similarity metric, where distances between doctors are either 0 for similar doctors or 1 for different doctors. But what about a general similarity metric? In our last result, we showed that if we remove any of the assumptions, that is, if we allow either a general similarity metric or unfair hospital preferences, no algorithm of the style of the Gale-Shapley algorithm guarantees both fairness and stability. We define a class of local proposing algorithms with a similar structure of the Gale-Shapley algorithm and to our propose and reject algorithm. These algorithms are local in the sense that there is no decision maker, and each participant acts upon their own preference without being aware to the preferences of the other participants. We show that no algorithm in this class can guarantee both fairness and stability. To conclude, we studied the problem of finding fair probabilistic allocations in the setting of the two-sided matching problem. We showed that under a strong fairness requirement over the hospital preferences and over the similarity metric, a fair and stable solution can always be found approximately using our algorithm. We also showed that if we remove even one of the assumptions, then any algorithm in the style of the Gale-Shapley algorithm fails to guarantee such a solution. That's it. Thank you.
Great, thank you, Gili. And so while we transition to another speaker, so Vijay is up next. If there's any questions for Gili, this is a good time to ask. Have you, so I know that there's a lot of experimental work on matchings or, applied to like real systems. Have you looked into this or like into running like an actual experiment, just out of curiosity?
In our research, no, but I know that there are works about real allocations of doctors to hospitals in Israel, but it's a bit, the setting is a bit different and they use a different mechanism.
I see. All right. Thank you very much. So our next speaker is Vijay, who hopefully will be able to share his screen.
I think it worked.
There we go.
But I have to, okay.
Great. So
everything seems to work somehow.
Our next speaker is Vijay Vazirani from UCI. Vijay, take it away.
Yeah, so I'm going to talk about, I'm trying to remove this bar from the top. Okay, I'm going to talk about matching markets, one-sided and two-sided in both Fisher and Arrow-Debreu settings, but all defined from a new angle in this paper, the Nash-Bargaining-Based Models. So basically, this is joint work with Mojtaba Hosseini, who's in the business school at UC Irvine, a very fine student who couldn't make it to this at this time because he's interviewing. So he asked me to give this talk, but he has given the half-hour talk that is recorded. And very nice one, that too. Okay, so the models we are considering here are those defined using cardinal utility functions, unlike the previous models which were defined using ordinal utility functions like the Gale-Shapley model. But here we are using cardinal utility functions. And these models suffer from two deficiencies. The first one is the following, and here I'm talking about a very classic mechanism given by Hyland and Zeckhauser more than 40 years ago, 79. And last year, it was realized that it is intractable. So computing even an approximate equilibrium for this model is PPAD complete. And the two works, one of them gave membership and the other hardness. So it showed PPAD completeness. And this is actually the most elementary matching market that one can think of because it's one-sided and it's based on linear utilities. So nothing could be simpler. Then Hyland and Zeckhauser did look at a further model, namely Arrow-Debreu extension of their mechanism and realized that it does not even admit an equilibrium. So they gave a counterexample, and that's where things stood for 40 years. Basically, there's no other models that we are aware of, in particular, no models for two-sided matching markets. And that's a very strange circumstance, because if you look at general equilibrium theory, it's replete with models, so many models, fundamental models that address highly specialized and realistic situations and more general situations and so on. So why this paucity? So our work is trying to rectify both these flaws, the intractability of HZ and the paucity of models. And okay, so before I go into our work, it'd be important to go a little bit deeper into Hill and Zecauser. It's a fantastic mechanism. If you really look at it, I fell in love with it for a very long time until the intractabilities came about. I was really hoping that because it's really a marriage between matching and the linear Fisher market, both of which have not only polynomial time but strongly polynomial algorithms. I was really hoping that since it just combines the two, it should lead to a polynomial time algorithm, but no, it's highly intractable. So here we have a one-sided matching market. So for instance, agents and goods, and only the agents have preferences. Goods are dumb. Okay, they don't have any preferences over the agents. Okay, so that's how a one-sided matching market works. And in particular, we have equal numbers of agents and the goods are indivisible. So you really have to find a permutation between these two sets. And Uij is a utility that agent I derives from good J. And of course, we want to not find any random permutation of goods to agents, but something that has good properties, like at least Pareto optimality, okay, or NB freeness, and so on. So Hill and Zecauser use the power of a pricing mechanism to achieve these nice properties like this. What they say is that we first make the goods divisible. So we have 1 unit of each good. We'll think of it as 1 unit of probability shares. Then we give $1 to each agent. And we make the demand of each agent be 1 unit of probability shares across all the goods, whatever they get, okay? And then we find equilibrium allocations and prices of goods. So definitely prices of goods will emerge through demand and supply considerations, and people will receive different probability shares of different goods, depending on the prices of the goods, and everybody has exactly $1 to spend. Okay, and this equilibrium, this allocation will actually be a fractional perfect matching over the n agents and n goods, or the complete bipartite graph, let's say, over n agents and n goods. And the way, but remember, I had said that in the original problem itself, the goods are indivisible. So the way you round these this fractional perfect matching to a real perfect matching, to an integral perfect matching, is to use the Birkhoff-von Neumann theorem, and that ensures that the expected utility that each agent got from their fractional allocation is the same as what they got after rounding. Okay, so so everything is very nice, and the mechanism has wonderful properties that come because of the power of the pricing mechanism, namely Pareto optimality and NB freeness and incentive compatibility in the large. Wonderful, and that's why it was a classic. I mean, nobody in economics wants to ever give up on this. And the problem, of course, is that it's intractable, and so intractable that at least I don't know of any way to solve even a small problem with n equal to, say, 5 without doing an exponential search over the space using algebraic cell decomposition, where every iteration takes so much time. So I'm saying this is a very, very conservative estimate. You cannot solve anything more than n equal to 10, probably not more than n equal to 6 or 7. I don't know. I don't know what n, but depends on how many mega computers you throw at the problem, obviously. So what should we do? It's totally intractable, totally unusable. All the nice properties are worth little in the real world, in practice. Okay, so here we have proposed Nash-Bargaining-Based Models. And so I first have to introduce to you the Nash bargaining problem. And the situation is that there are two agents who possess one good each, let's say a divisible good, and they want to exchange fractionally these goods. Okay, and you let S be the set of all possible utilities derived by these two agents through all possible exchanges. So on the one extreme, both goods are with one agent. On the other extreme, both goods are with the other agent. And in between are all other possibilities. And this is called the feasible set, the set S. And the property that we demand from the set is that it should be convex and compact, which is not too much. Okay. And besides this, the problem definition also has the disagreement point, which are the utilities that the two agents get by remaining at status quo. So C1 is what the first player got, and C2 is what the second player got by just when they came to do the bargaining. And obviously they will do the exchange only if their solution lies in this space. So C1 gets more, one gets more than C1 and two gets more than C2. Then only they'll do the exchange. But the important question is which point to pick in this region. Okay. And here's where Nash came in. I think it was, okay. Oh yeah. So Nash gave 4 axioms for saying which point. And these are all important axioms: Pareto optimality, which we always like, invariance under affine transformation, symmetry, that means the naming of the players should not affect the solution, independence of irrelevant alternatives, which is always nice. Also, no time to go into any of these details, but I hope you will read up on these if you don't know already, and most people would know already in this community. So then came the wonderful theorem of Nash, which is really, really elegant, so beautifully done, that there's a unique solution in S that satisfies all 4 axioms, and it is given by maximizing this product. V1 minus C1 times V2 minus C2, where V1 and V2, this vector V1, V2 lies in the set S. And obviously it will be maximized at the boundary, and so you'll get a Pareto optimal point because the boundary is convex. So, you know, and also the rest of the properties are satisfied. And in fact, it's through the properties that you prove such a fantastic theorem. And in fact, it works not only for 2 agents, but any number n of agents. Not only that, but because you're maximizing this product, if you take the log of this product, you get a concave function, which you are maximizing over a convex set. So the Nash bargaining solution, is the optimal solution to a convex program that already puts it in P. Okay, maybe at least to approximate it to any given degree. And so the very first thing that went wrong with Heel and Zekoser looks like we can do it, and indeed we can. So we can define a linear Fisher one-sided matching market by defining S to be the utilities derived by the n agents in all possible fractional perfect matchings, and let the Nash bargaining solution pick that the unique point at which the market will operate. And of course, yeah, so here the disagreement utilities are 0. Then there's the Arrow-Debreu extension, which is easy by taking the disagreement utilities to be initial endowments, and easily extends to 2-sided. Everything easily extends. Experimentally, we can solve n equal to 2000 in 1 hour over a laptop. Game theoretic properties come from Nash bargaining, but then NB-free is not possible in this setting. And there's a new paper coming up where we show proportionality, at least 1 over 2n fraction of each. Everybody will get at least 1 over 2n fraction of the total utility. And if you don't have unit demand constraints, which you have to have, it will be 1 over n, which was a well-known result from the past. And this is a principal move because it really, in a deep way, connects up linear Fisher setting markets with Nash bargaining and the Eisenberg-Geld convex program. And you can look up more details in the paper because I've run out of time. And the one question that we leave open is, are there combinatorial algorithms with proven gravities? And this paper that I mentioned gives the first answer to this question, but I'm sure there'll be many more answers to this question, and I hope many more questions because there are so many models to be studied here. Thank you.
Thank you very much, Vijay. So we're a bit behind on time, so we'll cut the questions for this, and if the next speaker can set up, so if you can stop sharing. And the next speaker is Kang-Ming, who's gonna tell us about interactive communication in bilateral trade. I'll start the timer. The floor is yours, Kang-Ming.
Thanks. So I'm going to present our work, interactive communication in bilateral trade. It's a joint work with Jieming, and Renato Paes Leme from Google. And I'm borrowing the slides from Renato. So we consider the bilateral trade game where we have Sally and Bob. We have two players. And Sally is trying to sell one item to Bob. And Sally has a private cost on that item. And Bob has a private value on that item. And in the end, Sally is going to choose a price P to price the item to Bob. And then Bob will accept the price if his value is higher than or equal to P. And finally, Sally's utility would be the price minus her cost if the item is sold. And Bob's utility would be value minus price if the item is sold. And in this setting, from the revelation principle, we know that interaction is not useful if the agents are strategic. And also from the Merage-Satterthwaite theorem, we know that we can't design games that are always efficient, meaning that there would be cases where value is higher than cost, but the agents will not trade. However, that's actually not really the case in reality. For example, we have jobs like car dealers and real estate agents that are primarily based on bargaining. So our goal of this work is to define models of bilateral trade so that we can capture this power of interactive communication. So to that end, we introduce a new ingredient of the classical model of Bayesian persuasion, where we have a receiver and a sender. The sender knows some state of the world, theta, but the receiver doesn't know the state. And in the end, the receiver will take some action, and then they will get the utilities based on receiver's action and the state of the world. And the persuasion part is, in the beginning, the sender can send some verifiable signal, sigma, that can be correlated with the state of the world to update the receiver's perception of the state. So that upon receiving the signal, the receiver can choose the action to maximize her expected utility given she has received the signal sigma. And there's an influential paper in this setup by Bergemann-Brooks-Morris, where they consider the setting where Sally is selling one item to Bob. In their model, Sally has a fixed cost, but Bob has a private value. So in this model, only Bob has private information. And in the end, Sally can choose some action by choosing a price P, and then Bob will accept if his value is higher than or equal to P. So for Sally, the best price to set is to maximize this price minus cost times the probability of Bob buying the item. And in their model, they have this, in the beginning, Bob can persuade Sally by sending a signal, and this sigma can be correlated with the value. So upon receiving that signal, Sally will instead choose the P to maximize price minus cost times the probability of Bob buying the item given he has sent the signal sigma. And their main result is that there is a way for Bob to send the signal so that the trade is efficient, meaning that if the value is higher than the cost, then they will always trade. And Bob will be the one to capture the remaining surplus from trade in this set. And we generalize their model so that Sally now also has a private information in the form of her cost drawn from some distribution. And we can still have the same model where Bob will send some signal to Sally, and then Sally will set some price. But we can actually have an even more general model by which we call Bayesian conversation, where in the first step, let's say Sally can send some signal, sigma prime, about her private cost to Bob. And then after receiving that signal, Bob will send something back to Sally about his private value. And finally, Sally will set some price. And we can generalize that thing into a T-round protocol where Sally sends something to Bob, then Bob to Sally, and so on. until in the end, Sally will set the price P on the item. So in this model, we consider the equilibrium concept as the subgame perfect Nash equilibrium. So the agents will use backward induction to select their optimal strategies in each step. And in our model, we have two assumptions. One is each receiver can always refuse to hear the signal of the other player. And another assumption is that ties are broken favorably to the other player. And for this model, we can define this message complexity. So for example, if pi I t dsdb means the utility for agent I in a T round protocol, first we can show that the utilities are always monotonically increasing, so that we can define the limit of the utilities. And then we can define this message complexity of a bilateral trade game as the minimum number of rounds, so that the utilities will stop improving after that point of T rounds. And our main result of the paper is that the agents won't stop communicating until they have reached an efficient allocation. In other words, if the message complexity of some game is finite, then it means we have reached an efficient allocation. So the utility of the seller plus the utility of the buyer equals the maximum possible gains from trade in the game. And the main open question in our work is that we have this conjecture that we conjecture the message complexity is always finite if the distributions have finite support in bilateral trade. So if that's true, it means our interactive communication model will always lead to efficiency in finitely many steps. And if that's false, it means there are settings where the agents would prefer to have an infinitely long conversation, and they won't trade before having this long conversation. And in our work, we also have a set result where if Bob's value distribution support has sets 2, then we fully characterize the communication protocol and show that a 2-round protocol is enough for efficient trade. And we conclude by having the following message, where long interactive communication can improve outcomes, and that often will lead to efficiency. Thanks for listening.
Great, thanks. And while Kang changes his slides, I want to ask quickly: do you have any? Do you have any idea for this conjecture, if it's true or false, after thinking about it?
Yeah, we actually think it should be true by running some experiments.
Okay.
So yeah, in general, a very small number of rounds should be enough for the bilateral trade setting. But for the more general game, in our work, we also define the same setting for more general games. And for more general games, we ran experiment, and it seems to be the other way, that like the message complexity can be infinity for finite support.
I see. All right, thank you. So if you can stop sharing, and our last speaker of today can share his screen. Terrific, thank you. So our last speaker is Konstantin Savarny from the Technion. He is going to be telling us about multi-channel Bayesian persuasion. Take it away, Konstantin.
Hello, I'm Konstantin, and I'm going to talk about multi-channel Bayesian persuasion. This is a joint work of Yakov Babichenko in Talgam-Cohen and Haifeng Xu. There are many examples in which a person tries to persuade a group of agents to act in her favor by revealing some partial information. One such typical situation is a politician trying to persuade voters. A standard mathematical model capturing this situation and many others is called the Bayesian persuasion, and we've already seen a variation of this model in the previous talk. So in the general Bayesian persuasion model, there's an agent called sender, for example, the politician, who aims to persuade some set of receivers, for example, the voters, to act in the sender's favor. They assume that each agent has a utility function, and also there is a certain state, the value of which is known to the sender but not to the receivers. However, all the agents have the same prior distribution on the values of the state. And a possible example of a state is the politician's plan. Before observing the value of the state, the sender should strategically commit to an information revelation policy, such as a political campaign, and we call this policy a signaling scheme. The current Bayesian persuasion literature mostly assumes a dichotomy. Either the sender may communicate with each receiver via a private communication channel, and this model is unsurprisingly called the private persuasion, or the sender must transmit the same signal to all the receivers, and this model is the public persuasion. However, in many real-life applications, it is reasonable to assume that the sender can communicate with different subsets of voters, or in general receivers, via different communication channels. And this is the model we study in our paper. Let's demonstrate our setting graphically through an example. So here we have 3 states with prior probabilities 0.3, 0.5, and 0.2. We also have 4 receivers and 3 communication channels: red, green, and purple. First of all, the sender commits to a signaling scheme, which tells for any possible state which combination of signals to send through the channels with which probability. After committing to the signaling scheme, a state is drawn from the prior distribution and is reported to the sender. Upon receiving the state, the true state, together with the signaling scheme, specify the signals the sender transmits through all the channels. And each receiver observes the channels which are sent through the relevant communication channels. So, for example, here, receiver 1 observes only sigma 1, while receiver 2 observes all the 3 signals. Upon observing the relevant signals, each receiver updates her belief about the distribution of the state to a certain posterior distribution using Bayes' law, and then each receiver takes an action aiming to maximize her expected utility over the posterior distribution of the states. And finally, each agent, both the sender and the receivers, get utilities which depend generally on the true state and on the actions of all the receivers. In Bayesian persuasion, the sender is the designer, and therefore, normally the research focuses on helping the sender to choose an expected utility maximizing signaling scheme. In our paper, we studied the most general Bayesian persuasion setting by allowing arbitrary structure of communication channels, as well as arbitrary functions of both the sender and the receivers, and also arbitrary prior distribution. Also, our model captures receivers who have externalities, which means that the actions of the receivers affect each other. Our main research question in this paper is as follows. When one communication structure is better for the sender than another, in the robust sense, where robustness means that the sender's preferences should hold regardless both of the utilities of the sender and the receivers, and also regardless of the prior distribution. And a previous work of Galperti and Perego studies an analogous question in a slightly different setting. To present our main result, let's introduce a simple notion of information dominance. We say that one receiver information dominates another receiver if the first one observes at least the same communication channels as the second one. So in this example, receiver 4 is information dominated by receiver 3, because receiver 4 observes only the purple channel, but receiver 3 also observes the purple channel. On the other hand, receiver 2 observes all the 3 channels, and therefore she information dominates all the other receivers. Our main result is that a communication structure M1 is better for the sender than another structure M2, regardless of the prior distribution and the utility functions, if and only if every information dominating pairs of receivers in M1 is also an information dominating pair of receivers in M2. Intuitively, each information dominating pair of receivers imposes restrictions on how much the sender can miscorrelate the signals intended to different receivers. And it turns out that such restrictions are the only restrictions. And quite surprisingly, the proof is based on secret sharing protocols from cryptography. One important special case is that in a communication structure without any information domain pairs of receivers, such as this example in the slide with 6 receivers and 4 communication channels, the sender can implement private persuasion. And in particular, private persuasion is the best possible communication structure for the sender because it's the most flexible. Communication structure. It also follows from our main result that a number of channels, which is logarithmic in the number of receivers, suffices for the sender to implement private persuasion, which is an exponential improvement compared to the naive implementation of private persuasion. And also our construction achieves the information theoretical lower bound on the number of channels required to implement private persuasion, and not only asymptotically, but also exactly. We also prove 2 computational results. On the positive side, we provide an additive FP-TAS for a natural family of communication structures and additive senders utilities. Here we only focus on a constant number of states because it is known from previous literature that for a general number of states, even public persuasion, even assuming additive senders utility, is hard to approximate. On the negative side, we provide a general family of senders utilities for which both private and public persuasion are computationally tractable, but general multi-channel persuasion is NP-hard. The main takeaway from this paper is a simple characterization of a partial ordering over the communication structures by the sender's preferences in the robust sense. The robustness means that the preferences hold regardless of the utilities of all the agents and the prior distribution. We studied some natural special cases, but of course, many other interesting cases exist. And it would be nice to understand the real-life applications of our model. And one specific case which one may study is the fixing certain utility functions for the agents and providing the sender with some communication structure, but allowing the sender to perform changes to the communication structure under some constraints. For example, to add the limited number of communication channels. And the question would be whether it's computationally tractable to understand the optimal sender's behavior in such a setting. Thank you very much for your attention.
Great. So a big round of applause to all our speakers. One quick question, Konstantin, while you're still here. So could you give some intuition as to why multi-channel is harder than both private and public persuasion?
Yes, so I can tell you all the functions. So there is a supermajority function, yes, which assumes that each receiver has only 2 actions. And if the number of receivers taking action 1 is above a certain threshold, then the sender gets utility 1, otherwise 0. So when we take weighted average of such functions over a partition of receivers, then it is easy to show that it is tractable for both public and private persuasion, but not for general persuasion. Yes, and the reduction is from the minimum union problem.
I see. Okay, that's very clever. Thank you very much.
Thank you.
So another round of applause to all speakers. Thanks again for being so accommodating, everyone, and sorting out the technical difficulties that we had. Thanks to our speakers, and there should be a link to gather, if you want to have more one-on-one questions or things like this. Thank you, everyone.